if we ran this and every single person in here did this, we're trying to see if they can taste different colors of Skittles. So today we'll conduct an experiment, perform a significance test to see if your class can really taste the rainbow. Obviously, in our situation, probably not true. But let's say that we ran this for everybody, right? Let's say we did out of the 150. Let's say that 97 were correct. Now, most of the time, it's probably a guess, right? I mean, let's be honest. I gave them back-to-back colors, and they still got them wrong, right? They told me different things. But what we're going to do is we're going to choose a procedure. So that's going to be a one sample z-test for P. Our alpha is 0.05. We started talking about this yesterday. Okay. Our parameter is going to be the true proportion, P, which is going to be the true proportion of correct guesses for all Skittles plus. And then for our statistics, so what we found in our study was that P hat is equal to 97 out of 150. And that's going to give us 0.647. Yesterday, we started talking about the hypothesis, okay? The null hypothesis was what? Like, define null hypothesis for me. Okay, so in here, we're trying to say that 0.2 is the true proportion. Okay, and let's say that HA is P is greater than 0.2. And we already have evidence for our alternative hypothesis because when we did our sample, we got let me try this again. We got 0.647.
Where do you get 0.2?
I'm telling you that it's 0.2. Yep.
So the probability is correct is 0.2.
Well, why would it be 0.2? How many colors do we have? Okay, so I'm going to have 1 out of 5. Does that make sense? Okay, so out of the 5 colors as an option, you're guessing 1 out of 5, right? Everybody good so far? All right, now we're going to check. You're going to do your random 10% and large counts. Okay, so let me get this to be a little bit bigger. So we're checking our conditions. So we've got random. Is there a random sample of Skittles? Yep, random sample. Wow. Wow. Let's show again. Random sample. Okay. That means that we can generalize to all Skittles, right? Okay. Now for 10%, that's 150, which is less than or equal to 10% of all the Skittles in the world. So sampling without replacement is okay. Otherwise, y'all would have to regurgitate every Skittle. That would be kind of gross. Okay. And then large counts. Okay. So we got 150 times that 0.2, which is equal to 30, which is greater than or equal to 10. And then we got 150, 1 minus 0.2, which is 0.8, which is equal to 120, which is greater than or equal to 10. So then we can do approximately normal distribution. One of your multiple choice questions on your AP Stat exam is going to be about the conditions and what you can do because of that condition. So generalizing it to the population. the sampling distribution is going to be approximately normal. Sampling without replacement is okay. You need to know those three things. Okay, so every time that you write it down, that's what you need to be thinking about. Yep. Uh-huh. So your sample is without replacement.
So if it's not almost 10%, then it's so easy.
Right.
Then next time we do.
It's got to be bigger than 10. And it's approximately normal if that happens. Yeah. Okay. If conditions are met, we're going to perform the calculations. So what's the general formula for this? We talked about this yesterday. Remember, this is the same thing as z-score. We're just calling these things a little different this time around. So we're going to say statistic minus the parameter divided by the standard deviation. Standard deviation. And this formula looks a little stupid. I'm sorry. So z equals p hat minus p divided by the square root of p times 1 minus p divided by n. I do want to point out that when you write this formula, you're using p, not p hat. Okay, for the standard deviation. So you're using p, not p hat. Okay, it does make a difference. Now you're using 0.2 versus 0.647. Okay, so now we're going to plug in the numbers. And this is going to give me z equals 0.647 minus 0.2 over the square root of 0.2 times 0.8 divided by 150. When we type all that junk into our calculator, you're going to get 13.68. Okay, so 13.68 is our test statistic. That's what we call Z. Is that on our table? So what's the likelihood of that happening? Ooh. P-value is going to be equal to 0. So when you do your normal curve, and draw the normal. Ooh, get my name off of there. That would be cool. Nope, I didn't want to make this bigger. Get away. Okay. So when you draw the normal curve, what's your mean? Or what's your middle? 0.2. And then we found 0.647. Right? Go ahead. Our curve probably is not a good representation of what's going on. But we don't figure that out until after we found the z-score. Because 13.68 standard deviations away from the mean. So the p-value is going to be 0 because it's not likely to occur at all. Yeah? Okay. All right, making a conclusion in context of the problem. Okay, so when you do your conclusion, you need to interpret the p-value, interpret p, and your decision and conclusion are the last part. So interpreting p, we're going to say assuming that the HO is true, p equals 0.2, there is about a 0 probability of getting 0.647 equals p hat or greater purely by chance. So remember how terrible we did in our like real classroom example? Like out of the 15, we got 2, right? Is that anywhere near 0.647? No. So the likelihood of this happening is like super tiny. Like 0, right? Like even if Mo sat up there with like 40 more Skittles, probably not gonna do any better. I'm not doubting your abilities. You get like 2 out of like 40. It's okay. We're not judging. I couldn't do it. I'll just be honest. They all taste the same. All right, now decision and conclusion. Because 0 is less than 0.05, do we reject or fail to reject? Do you remember? It's less than. You don't make enough money, so we reject the HO. And do we have convincing evidence? Or do we not have convincing evidence? We do have convincing evidence that this sample, the 0.647, that the class can taste the rainbow. Now, obviously, we didn't run this experiment because I don't want to, A, give you a cavity, and B, we would be here a really long time. But if we had our sample be 0.647, then we would have convincing evidence. Okay? If we went based off of our 15, like our sample of 15, then we would not have convincing evidence. Does that make sense? So, but this is not enough data in order to actually make this happen. Yes. H of O. HA is the alternative hypothesis. Good. All right, we'll go to the back. We're going to summarize. Yay, what did we learn? Okay, still have the whole process of the choose, check, calculate, and conclude. And we chose a procedure, parameter, alpha, statistic, and hypothesis. So when you do choose on this one, you're like stating all of the information. Procedure, alpha, it looks like a little fish. Alpha is 0.05. Parameter, statistic, and hypothesis. You're going to check the conditions. You're going to write the general, the specific formula, plug in, do a picture, do a p-value. Like in the calculate section, you want to act like they don't know what they're talking about when they're reading your thing. We did the normal distribution. Gotta draw the curve. If the conditions are checked and large counts work, you can draw the normal curve. That's your picture. Okay. And then for conclude, we're going to interpret and decide. We also talk about two-sided, where we had the alternative hypothesis, which P does not equal the null value. And when we have a two-side, we can multiply our p-value by 2. We haven't seen this yet, though. So what I want you to do is you're going to do the next problem. Choose, check, calculate, conclude. You should at least get through the choose, check, and calculate part. I'll help you with the conclusion in just a second. So go ahead and take some time. Yeah.
Like, how to ask for a picture and also like I know it's not accurate, but you're still gonna take it. What if I just draw a star? It's like a little good star.
Victoria, you're thinking with logic. That's not welcome here. All right, let's get it started. Okay, so CNN once claimed that half of teenagers are addicted to their phone. Half. All right, a random sample of 180 teenagers was selected, and 72 reported that they were addicted to their phones. Is there convincing statistical evidence that the proportion of all teenagers who are addicted to their phones differs from 0.5, use alpha of 0.05? Okay, so we're going to choose, and that's one sample z-test for P. We have our p-hat is 72 divided by 180, which is going to give me 0.4. What does P represent? The true proportion of teenagers addicted to their phone. What? You can put all teenagers. All right, so our HO is 0.5. Okay, because they tell us that. Our alternative is that it doesn't equal 0.5. Make sense? Evidence for HA is that the p-hat, which is 0.4, doesn't equal 0.5. Good? Say again?
The last word, it won't have to be.
You have to have evidence for your alternative hypothesis. All right, so now we're going to check. We're going to do random. So it literally states random sample of 180 teenagers. Okay. Your 10%, well, 180 is less than 10% of all teenagers. Your large counts, 180 times 0.5 is 90, which is greater than or equal to 10. 180 times 0.5 is equal to 90, which is greater than or equal to 10. So we can normally distribute. Okay. Now we're going to calculate. So now you're on to calc. And so test statistic is the statistic minus the parameter divided by the standard deviation. So we got z equals p-hat minus p divided by p. There we go. Square root of p times 1 minus p divided by n. We plug in 0.4 minus 0.5 divided by square root of 0.5 times 0.5 times divided by 180. And that gives me a z of negative 2.68. Now, we've got to find the p-value. We go to our table. We find that it's 0.0036 or 37, right? Okay. Why would we multiply it by 2?
Oh, right.
Why?
Because it would be less than or more.
Could be more less than or more than, where it could be not the null. Okay, so here it is again. 0.5 is the null. It either is less than or greater than. It could be equal to. If it's equal to, then our hypothesis is true, right? So that's going to give me 0.0072. We draw our lovely curve. It does not have to be perfect. First of all. Okay. Voila. Excuse me. Thanks. Thanks. 0.0072. And then now we're going to conclude. In our conclusion, remember, we've got to interpret what P is, and we got to make our decision and conclusion. So, conclude. Assuming that the HO is true, P equals 0.5. You know, whenever I write these out, I always think of it like as like a really sassy argument. Assuming that that is true, you know, that's what your conclusion kind of is, right? Kind of like you're gossiping to somebody. I don't condone bad words and I don't condone gossip, but here I am. Okay. All right. Probability of getting a p hat of 0.4 or lower or 0.6 or higher. Because if it happens on the downside, it can happen on the upside, right? Like the 0.4 and the 0.6, purely by chance. Now, because 0.0072 is less than 0.05, what do? They don't make enough money, so we reject the HO, okay, and have convincing evidence that the proportion of all teenagers who are addicted to their phone differs from 0.5. Yikes, man. Kind of makes sense. So, number 2, a 95% confidence interval for the proportion of all teens who are addicted to their phone is 0.328 and 0.472. Explain how the confidence interval is consistent with the significance test. So, our HO value is 0.5. Is that in between those two numbers? No. So that's why we reject the null, just like the significance test did. Does that make sense? Differs from 0.5. Sorry. So on number 2, the null value is 0.5, which is not contained in the interval, so we reject the null. Everybody good?
I think it's learning about ways to reject no.
Reject and fail to reject. Yep. All right, go ahead and take out your homework. Go to your 9.3. I'm going to give you a little bit of time to do it, about like 10 minutes, like not long. Okay. So take out your 9.3. Remember, tomorrow, 9.1 and 9.2 are due. So if you haven't done those, I'm giving you about 10 minutes in class to get them done. Or ask questions if you need to. Okay. And then we're going to go back and do 9.4 in just a second. Okay. Like I told you to play a card game. Yeah, this is where it comes into play. So in this simple card game, the dealer shuffles the cards, and the player randomly selects a card and has to predict if it'll be red or black. The player then returns the card to the deck, and this process is repeated until the player has done 20 selections. Lindsay claims to be better than Luke at this game. Lindsay plays the game and then gets 14 correct out of the 20. Luke plays the game and gets 10 correct out of the 20. Boo, Luke. He sucks. Luke believes that they are both equally skilled, that this result happened purely by chance. What a sorry loser. All right, so does this result, but really, right? Okay. Did you say no? Why? Who knows? Does the result provide convincing evidence that Lindsay is better than Luke at this game? So identify the statistic in the parameter. We are now moving into like what we just did in the last little unit. We're now going to find the difference of the proportions. Yeah. So we're comparing these two. If we're comparing two different people, we're going to subtract them. So we're going to say p hat 1 minus p hat 2. Oh, how much did Lindsay have? Which was 0.7 minus home skillet, Luke. And that's a difference of 0.2. Good so far? Now, parameter is going to be P1 minus P2. That is the true difference in proportion of correct guesses. And we did Lindsay minus homeboy. Homeboy. All right, two possible explanations for why Lindsay did better. Lindsay and Luke are equally skilled. That would be the null. So that's the null hypothesis. That means that P1 minus P2 would be 0. There would be no difference, right? Or Lindsay is better than Luke. Okay, and that would be the alternative hypothesis, which would mean that P1 minus P2 is bigger than 0. Go so far? Okay, so to test Luke's claim, we will assume number 1, they are both equally skilled, just simply guessing, and find the probability that these results happen purely by chance. Okay, so play the game with a partner, each person making 20 selections to determine a winner. Repeat the process again for a second time. Okay, go ahead and take a moment. You're going to turn to your partner. Okay, I want you to put a number behind your back, like 1. Well, that's not technically even. 1 or 2. Okay, and so what you're going to do is try to get the correct number of guesses. Okay, if you have 1, like behind your back, and they say 1, then that's correct. You're keeping a tally of that. You're doing it 20 times. Ready? Ready? 1 or 2, because red or black. All right, ready? Go. 1 sample. Oh, I'm sorry. 2 random samples is each dot, right? Like each one of you would have been doing it. It should be 2 random samples because it should have been like the difference between the 2. You're playing with a partner and you're finding the difference between you two. I bet you didn't do that part though. That's okay. You did? Not everybody. See, don't trust you with samples anymore. So it should have been 2 random samples of 20 cards and the difference of proportions of correct guesses. Okay, so today you have pride. Shh. Today you have pride. You also have homework if you didn't get your 9.1 and 9.2 done. Okay, remember you're turning that in tomorrow. It should be getting easier the more you do it. Yes? Yes, yes. Okay. All right. The next test is on the 28th. Okay, we're gonna try to quiz drastically before the test. Yes. Testing tomorrow. I think that's next week. Am I stupid? Is that wrong? Hold on, let me look that up.